just here a couple of hours ago to tell you all that we were doing with taking the vision for NGMM forward. And I just want to say a sincere thank you. I have had an absolute blast over the last couple of hours having an opportunity to engage with this community, hear your thoughts, get your feedback, and share your perspectives on where we're headed. It has just been amazing the last couple of hours, so thank you very much. I managed to just get a sandwich in along the way from all the communication. So anyway, I really, really appreciate it. It's been fantastic. Yesterday when Whitney was up here during the MTO 101 session, she said that occasionally we turn on the MTO bat signal and raise that bat signal up by way of a request for information or RFIs. And for those RFIs, we're really looking for feedback from the community to help inform programs that we're working on putting together. And this morning I talked to you a little bit about this concept that we have for a design challenge for NGMM, where we want to engage the community and find out what innovative ideas you have for leveraging that capability moving forward. And so it's almost like I planned it, but I'm super excited to come back a couple hours later and now have a fairly formal way through the RFI to ask for your input and feedback. We've got these RFIs that are pulled together that myself and my colleagues will talk about here over the next few minutes, and we expect to have these up and live by Monday. So here in just a couple of days, they should be up and ready and posted for your feedback. So specific to NGMM, I really want to ask again for your ideas about how you would leverage this capability, how you would utilize this stable, domestic advanced integration facility and what ideas you have to do so. And so in our case for the RFI, we really would like to ask you a few questions, plan to ask you a few questions about commercial and dual use applications, interests that you have, opportunities certainly for defense applications, but again, broadening out to look at commercial and dual use. We really would like to get some feedback from you about the kinds of architectures you're thinking about, the kinds of materials that you're interested in building these systems out of, and really what your integration strategy would be to pull them together to build these kinds of systems, as it sort of feeds in and informs the direction we're headed and will help us as we start to frame out what this design challenge is going to look like. Really also interested in different applications and creative ideas you have. As I mentioned this morning, we have this initial technology roadmap with these integration processes that are there. But our intent is not just to build applications that are aligned with those exemplars that I mentioned this morning, right? We really want to look much broader than that. And so that's why we really want to solicit some ideas from the community in that space. We also want to hear about the design and validation strategy that you would take to implement this system. We know that procuring these components, particularly in this mixed signal space with mixed materials, there is a very diverse supply chain, and so we want to get some feedback from you about approaches there for collecting those. And then the last thing that we'd really like to get some input on is, this morning I presented to you this kind of high-level technology roadmap that's built upon those exemplars, but we're also interested in getting some feedback from the community that we don't intend for that roadmap to be a stagnant thing that doesn't change and doesn't shift in the future. And we want to be informed and be thoughtful about the kinds of technologies or processes that we would add to that roadmap over the next few years. And so we intend to ask you for some feedback through this RFI about the suggestions that you might have for how we would evolve that moving forward and how that would intercept with the ideas that you have that maybe we could build within GMM. So with that, thank you very much. I'll hand off to the next, and appreciate again all the conversation today and look forward to some additional conversation this afternoon. Thank you all.
Next up, please welcome Dr. Wonin Jung.
Hello, everyone. Thank you for being here. So where our team is ensure, can you see the slides? Oh, maybe, it'll show up. It'll show up. So we're actually issue RFI. I think a very similar topic I talked about earlier in my talk yesterday. We're interested in really think about chemical resilience in our devices and the system. We want to interested, the devices can explore different really extreme requirement. And in this particular case, we're thinking about a very chemically harsh environment, right? Because our devices is very, as good as the environment can tolerate, right? So currently, a lot of microsystem devices is really vulnerable to acid and the base, salt, and even different kind of reactive species in the environment. How do we design devices that we can actually to be really resilient in this kind of really harsh chemical environment, that can survive, right? But obviously, traditionally, method you would think, there will be some the really extreme packaging approach, right? we're open to that. If you have, if you think you have a really interesting packaging approach, we're interested to hear that. But also on the flip side, my team has been thinking about, design, system design, right, device design. So maybe our environment is not really a foe, right? Maybe it's our friends, right? Can we, from a engineering perspective, from a design perspective, when we design the devices, right, can we actually think about the environment first, right? Maybe those environment actually can enhance what we do and enhance the device performance, right? Earlier in my talk, I think I mentioned that the example I use is actually in diamond synthesis, right? We think high temperature and pressure is really bad, right, for a lot of things. But when we synthesize diamond, right, we actually use high temperature and pressure to get the really desired property, right? We can use that kind of framework to think about, how we design devices. And in the RFI, you can actually read a little more detail too. We're interested also like different user cases you can think of, for, a chemical harsh environment, some like state-of-the-art metrics, and all the details and we have already talked about in this particular RFI. Right. We'll really appreciate your help and your input and to explore this space in a very deep way. Right. Thank you very much.
Next up, please welcome Dr. John Hoffman.
They all pass me by.
Good afternoon, everyone. Thank you for staying till the bitter end. For those of you who don't remember me, I'm the other John Hoffman in MTO, and I'm going to talk a little bit about an RFI we're issuing on one of the two topics that I discussed yesterday. The first topic that I discussed, which is the focus of this RFI, is on the opportunity space for sequence-defined polymers as being new materials that could give unprecedented performance advantages to the microsystems of tomorrow. These are the photonic, quantum, and organic devices of tomorrow. And so in this RFI, we want to better understand that entire opportunity space. And I'll take a few minutes here to talk about what I think that is. So the first part of that, of the space that we're looking at are new approaches to synthesizing these molecules. So yesterday I talked about existing nature's machines, which you see an image of here in the slide. This is the ribosome. We also talked about existing synthetic approaches. I provided a vision for a new to nature molecular machine that could also potentially synthesize these types of polymers. So the first part of the RFI that we'd like your feedback on is to really understand what are the new advances today that make us think we can generate these types of polymers. What are the synthetic approaches, and what are the risks and challenges around realizing these new capabilities? But moving a little bit past that, we see this as a potential platform technology, meaning that one specific synthesis route, whether it's one of these machines or a traditional synthetic approach, could be used to synthesize polymers with almost any backbone chemistry, or using this wide variety of monomers that we have available to us. And so another piece of information I'd like to get from the RFI is your feedback on what are the attributes of a platform? What sort of design capabilities do we not have today that we would need to make this platform a reality? What sort of build, manufacturing, synthesis capability do we need? Are round bottom flasks the right way to go, or is there automation that could help us improve the throughput of that process? And on the testing side, what types of instrumentation do we need to have in line to help us characterize the machines themselves or the synthesis route themselves and their products? Again, how can we do that in a high throughput fashion? And then the data that comes out of those, those tests, how do we format that data? How do we organize it in such a way that it can be fed back into our design stage and we get the maximum benefit out of the data that comes out? So that is the kind of the one axis that I'll call it of our idea. this platform technology. But then moving forward, what are the potential applications for these materials? If we could develop any sequence-defined polymer that we'd want, where do we see the advantage of those materials in the photonic, organic, and quantum systems of tomorrow? For myself, I've seen a lot of work in organic electro-optic materials, polymer-based materials that are aligning chromophores under electric fields. Are there new ways to use these sequence-defined polymers to have more interesting effects than we see from the existing organic materials? But going beyond that, quantum circuits, especially the organic devices, do we see new types of devices with these materials that we've just never seen before? And let's see, pardon me, and I think that's it. So yes, if you have any information that you'd like to share, we'll have the request soon, and I thank you for your input. Thank you.
Next, please welcome Dr. Jonathan Hoffman.
Good afternoon, everyone. I'm John Hoffman, not to be confused with John Hoffman. I'm really excited today to talk to you about an opportunity on our RFI on quantum manufacturing. Really, I'm here looking for your help. We know that quantum sensors have taken the most exquisite measurements of time, frequency, electric field, magnetic field, acceleration, rotation, and gravity. But today, they are still bespoke sensors that are not proliferated in the world. And what I want to figure out with your help is how we can actually transition this from the most exquisite sensors built in a lab to actual commodity products. So I'll walk quickly through this slide. What we're plotting on the y-axis is the relative performance of various quantum sensors. And on the x-axis is a manufacturability figure of merit. Now, you should 100% question this figure of merit. I have chosen the figure of merit to be parallelized units out divided by labor hours divided by touch points. And what we see is in the upper left, your one-off laboratory devices were great performance, but they're not out and products yet. And in the bottom right, the kind of devices you'll find on your phones. And what we do today is make some exquisite devices that operate as bespoke Swiss watches, or created as bespoke Swiss watches. And that's pictured in this middle center corner here. And what we want to figure out is, what are the things we need to do to make these quantum sensors commodity devices? And this is not just in terms of the device design, but I'm interested in what those manufacturing figures of merit are. How do we make the choice in how we design so that we can see a scalable future? Additionally to that, once we understand that manufacturable figure of merit, I want to understand what tools, designs, and devices we should be building. I think that there's a lot of opportunity here to think about how we actually build our devices to holistically integrate the qubit housing, the qubit preparation, and the qubit readout. So I'm really excited for this to be announced, and I really look forward to all of your feedback on how we can take quantum sensors from bespoke Swiss watches to commodity products. Thank you.
And now please welcome Mr. Dan Ridge.
Thank you, Spark Tank. And thanks for that Herbie Hancock walk-on music. It's further evidence that we make amazing stuff in the United States. So one of the things that I am keenest to know is, what if microsystems manufacturing in the United States was not an economic issue, but an existential issue? And so this is what I'd like your input on. And particularly, I'd like to hear about four things. I'd like to know about non-obvious products that, if repurposed and adapted, would better enable us to manufacture some type of microsystem in the United States or repair our substantial library of existing microsystems. I'm interested also in processes, non-traditional processes, print processes, additive processes that can achieve tolerances of, say, 2 microns, and which are capable of supporting production of 10,000 units of some type a year. And these are processes that I imagine are not used today for microsystem manufacture directly, but are used for biological processes, that are used for chemical manufacturing, but which could be adapted to this purpose. The third thing I would like to know is, and this is one where I think we can use particular help because the scientific literature is not helpful to us, which is facilities in the United States that are underutilized, that are in production for some other purpose, or which have been recently decommissioned and which can be very rapidly adapted to microsystems manufacture. And that's something where we absolutely need the public's help to identify some of these facilities. And I think that we're interested in facilities at a variety of scales, and particularly facilities that are at risk from other transitions to support realignment of industry and economy. The fourth is equipment and tooling, and I think that this one is an area where this may be even a thing that we know within our existing base, and we haven't thought to combine it, which is chemical manufacturing processes that are adaptable to the microsystem market. I think we have a lot of high precision biological manufacturing facilities that could be adapted relatively rapidly to microsystem manufacturing. And for all of these, I think we're interested both in the case of repair and manufacture. And I'll add further that something that's come up just through the terrific collaboration that we've had here at Spark Tank is a form of repair is the ongoing maintenance of health. Are there existing tools, facilities that will allow us to provide pacemaker-type curative treatments for legacy microsystems that we need to continue to operate while we bring a new generation of technologies online? So if you have thoughts about that or know people who do, we are looking forward to hearing about them and taking them very seriously, however non-intuitive they may be, especially how intuitive we hope they'll be. So thank you very much.
And now welcome Dr. Julian McMorrow.
All right, thank you. Good afternoon. First, I would like to thank all of you for the overwhelming response that I got to my talk yesterday. I was so unaware that people were so passionate about supply chains. So the fact that I had a lot of people come talk to me and I had a lot of great conversations, thank you. And I hope we can continue those conversations. I gave you all my contact information, so that'd be great. As a follow-up to the first topic that I talked about yesterday, the supply chain problem, the logistics problem, I'd like to at least reiterate a couple examples that I gave, and one of them was the Russian sanctions and their ability to circumvent sanctions with repurposed electronics, and then the other was COVID, what happened during COVID and our supply chain problems, and how certain companies were able to actually move product because, again, they repurposed electronics, right? Those are relevant to the RFI that we're announcing now. I think we'd really like to learn more. We have those proofs of existence proofs, but we'd like to know what you guys know. So the title here, what if TSMC fell into the ocean? That is perhaps a bit sensational, but earthquakes happen, COVID happens, so it's not inconceivable that we would be completely cut off from the most advanced microelectronics in the world, right? If that happens, then what? What are our brilliant ideas? What are our crazy ideas that get us out of that particular mess, right? So within the RFI, the RFI is titled Microelectronics Black Start. And within that RFI, we break it down into three categories of information that we're seeking, right? So one is what we call a black start capability, where an entirely new microelectronics manufacturing capability can be rapidly established at a location of choice, preferably remote, right? So this in some ways aligns with my marine on the beach scenario, but we have talked to, or I've spoken to, for example, microfab companies, the people who put fab lines in a shipping container. I think that's in scope here, but I'd really like something crazier. A little, what are your wild ideas here? So if you have ways of manufacturing advanced node electronics in a remote location, I want to hear about it. The next category would be a brown start capability where existing microelectronic supplies can be repurposed while manufacturing capabilities are existed and or reestablished to reach needed capacities, right? So in the example that I gave you during COVID, that they made use of a major consulting firm that created a database of who had certain, where you could find chips out in warehouses and what companies had chips, and then they started doing matchmaking. That seems like perhaps a very inefficient way to do it. It was definitely necessary and useful then, but I think we can do better, right? So again, this repurposing very much aligns to stuff that I talked about before. But then, if we're talking domestic, we have fab lines, right? But they're perhaps not at the most advanced nodes. Are there augmentations that we could do to bring those up to higher capability? I'd love to learn more about that. Then finally, for something more out there, clean slate capability where traditional microelectronics are replaced with unconventional technologies, thereby creating an entirely new and alternative technology ecosystem. So I recognize that there's at least a little bit of overlap with what Dan just asked for. So if you want to respond to both, you are more than welcome to. But take clean slate to be what you want it to be. Like give me some crazy ideas, and we can work with that. Okay. So I think that's all I have here, and I really look forward to your responses. Thank you.
And finally, please welcome Dr. Justin Cohen.
All right, hello. Save the best for last. Thanks for waiting. Okay, so if you were here yesterday and had to listen to me geek out about quantum photonics, then I'll be bringing up some pretty similar concepts here. But while yesterday I was really upbeat about a lot of the really exciting directions that I think we can take this, what I'll talk about now is some of the things that I'm actually really concerned about long term for being able to realize and commercialize these technologies long term. And this concern kind of is a combination of a technology problem and a business problem. And it really comes down to the fact that when we talk about quantum photonics, it's not just one thing. There are a huge number of different atoms, color centers, ions, defects, different quantum emitters, different quantum matter resources that people have all sorts of great ideas about how to develop into new sensor technologies, into new quantum compute platforms, various different quantum technologies. And each one of those quantum resources requires some pretty spiffy component requirements, whether these are modulation, filtering, isolation, different laser powers that we need to drive a given wavelength to interact with an atom in a certain way. And it's not just as simple as there being a huge variety of components, but the components needs are going to be different for every other atom. There's multiple different wavelengths associated with every atom that are different from all of the other atoms. And so when we think about someday eventually being able to commercialize these technologies, how are we going to fabricate them? If we want to be able to leverage the power of semiconductor fabrication and photonics foundries, there's a big gap in being able to say that any one of these atoms is going to drive enough volume for the economies of scale of a foundry to make sense. So what I would like your help with, especially if you are a company trying to commercialize a quantum technology, is please tell us what are your pick needs and what is your wish list. And if you when this RFI comes out, you'll see we kind of are asking for a lot of detail, like here, what is the list of components, what is kind of threshold and objective performance that would really be enabling to open up markets and opportunities for these technologies. And the way this can help us, and that I hope can help you, is if we can aggregate all of these inputs and find out about whether there's a future photonics platform that we can go push to develop that can serve large swaths of the needs across these different quantum resources, then maybe we can have a program that goes and develops that and aggregate enough demand across the ecosystem, across the industry, to make this economy of scale with foundry production make sense, and ultimately let us get to a place where businesses and foundries can thrive and capture this capability for the United States, so that we can continue to advance it and get it into the right hands. So I hope this is just the beginning of a conversation, but any inputs that you can provide for us to really quantify these needs could really help us help each other. Thank you.